Welcome to this ninth lecture for Physics 4B. In this extra lecture for this week, we will review some mathematical content that you may have seen in earlier math class or in Physics 4A. But I find that many students can benefit from some timely review. As we consider electric fields in 3 dimensions and start using the dot product in important calculations, now is the right time for a timely review. And later on, especially as we start on magnetism in a month or so, if you find that you need another review of vector topics, this is the one lecture that is meant to be a comprehensive review of all vector-related content for this class. So, in the first video, we start with an overview of different coordinate representations for vectors, especially in 3 dimensions. This is material that you may have seen in your multivariable calculus class. Please note that physics convention for angle symbol is different from the common math convention for spherical coordinate system. We use theta to indicate the polar angle, the angle between the vector and the z-axis, and phi or phi to indicate the azimuthal angle, the angle between the x-axis and the projection of the vector onto the xy plane. In the second and the third videos, we review the dot product and the cross product. If you have taken Physics 4A here at College of Alameda, you should find that all this was covered in Physics 4A before, perhaps with the exception of the mention of the Levi-Civita symbol. In this second view around, I hope your understanding of vector products deepens. We will use all this material, with the exception of the cross product for a month or so, in our regular lectures this week, covering more calculations involving 3-dimensional electric charge distributions and vector products, as we introduce electric flux and Gauss's law applications. So let me call this, I guess mathematics overview is a bit too vague. Maybe this is the way to title it. Let me call it coordinate representations and product of vectors. So let me start out with the coordinate representation. That's probably the most intuitive part that we can start with. So let me start out with something that kind of refers to what I did on Friday and something that I think most people are familiar with. I hope you feel comfortable working with 2-dimensional stuff with the XY coordinate system. And if you have a point in this plane, it could be this point. Let me just label a few different points. So we could be talking about this point in the first quadrant, or we could be talking about this point in the fourth quadrant, or we could be talking about this point in the second quadrant. Or you can be talking about a collection of points. And when you have these different locations in space you want to represent, the Cartesian representation is very intuitive. You have the axis, you basically drop down a perpendicular line to your axis and you read off the numbers. That's what the Cartesian representation is. And something that you have learned, I think usually in trigonometry class, is the polar representation of these points. So for the polar representation, what you're imagining for each one of these points is you imagine describing them not by components, x and y, but by distance and direction. So for this point, my P1 here, I might have this distance R1 and this angle here, theta 1. And the same deal with all these other points. So my point 2 might be described as, I can make my angle go either direction. I can definitely have my angle go in clockwise direction, theta 2, and this would be considered a negative angle. Or I can go the other way with the angles. Sometimes there's more than one way to get to the same place. And so this point would be at a distance r2 at an angle theta 2 measured from the positive axis. And my point 3 would be at distance r3 at some angle theta 3 from the positive x-axis. And you might remember the relationship between these two ways of representing your point in space. So if you are starting out with your component description, then you can say my distance that you can get from Pythagorean theorem. This is a right triangle with the legs x1 and y1. So the hypotenuse of the triangle will be given by, or I guess this is the Pythagorean theorem. The hypotenuse squared is equal to sum of the squares of the legs. Or if you're solving for r1, it'll be square root of x1 squared plus y1 squared. So that's the distance, comes from Pythagorean theorem. And as for the angle, the most common way we express these angles is through the trig expression. So tangent of the angle is the opposite side over the adjacent side. It involves only the components that you already know. So we can say tangent of theta 1 is y1 over x1. And in fact, this is the representation I prefer over the version that might say theta 1 is equal to arctangent of y1 over x1. And that mainly has to do with some ambiguity in this expression because of the way arctangent function has to be defined. For example, in this version, there isn't an easy way to tell between a point that's in the first quadrant and a point that's in the third quadrant, because the ratio of y1 over x1 is always positive, whether they are both positive or both negative. But this expression, so it doesn't make a judgment call on which quadrant your angle must be beforehand. It's another exercise you have to go through to figure out if your theta 1, which gives the ratio of the components, is whichever quadrant it's in. So anyways, so this is a way you might relate, starting from the component expression, how you might go to the polar representation of your point or your vector. This is actually what we could easily call a vector, although it's probably only in physics class where you see that explicit reference. And you can also go the other way. If somehow, if you are given the distance and if you are given the polar representation of your point or of your vector, then you can represent it kind of the way you have been doing in physics 4a when you work through a force analysis question and you have to break forces into components. So here, all I have to do is break this vector into x and y component. And when I do that, my x component is r1 cosine theta 1, and my y component is r2 sine theta r1. Sorry, I shouldn't have done that 1, 2, 3 thing. r1 sine theta 1. So this is the way to get from the polar representation to component representation. And one of the things that you learn in trigonometry class is these theta 1s, they can actually take on any value. They don't have to be an acute angle. They can take any angle from 0 to 2 pi, or they can even be greater than that, and it'll all work out. These expressions are valid for all values of thetas and the positive values of r. R is only allowed to be 0 or positive. So this is a review of something you have seen. Nothing new, nothing surprising here. And I wanted to start from here to expand into coordinate representations for three-dimensional space. And so in physics 4a, for most of the class, we have only dealt with two-dimensional representations. It's because even though we live in three-dimensional world, very often you can find a suitable plane so that all the interesting stuff only happens in a two-dimensional space. There were some exceptions when you do rigid body motion and deal with the rotation and angular momentum, then you have to bring in three-dimensional space. But with those small set of exceptions, you could deal with it, just dealing with a subset of your space. That won't be the case in electromagnetism. That's frankly the reason Math 3C is a core requisite for this class. If I could, I would make a Math 3C prerequisite, but I know I can't, so I didn't try. It's in your multivariable calculus class when you learn to deal with the three-dimensional space more fully than you have learned to do in your other classes. So let me first start out with the coordinate representations for our three-dimensional space. And I guess the place to start maybe is to first describe a projections space, or let me first start out with the xy axis first, and I'm going to define my x and y axis so that it defines what looks like a horizontal plane. So, and I'm drawing it in perspective view. So drawing my x and y axis in perspective view, it would look something like this. You have to imagine you are kind of staring at this from over a plane, and x-axis is coming towards you, y-axis is going to the right. You'll see why I'm describing those directions in that a bit of an unusual way. I guess, yeah, and I guess I could describe this as x and y, but somehow I think it's less commonly drawn that way. Let me just go with how it's usually drawn. So when you're drawing three-dimensional axis, we are limited by the fact that we are working with only two-dimensional drawing. So we'll have to have some convention for properly representing these three-dimensional points. Let me draw the z-axis. I need my third dimension, and with my x and y-axis drawn this way, my z-axis has to point upward. The constraint on my z-axis is it has two constraints. One is that it must be perpendicular to my other two axes. So my z-axis is perpendicular to my x-axis, and it's also perpendicular to my y-axis. That's one constraint. And the second constraint, what I have drawn here is what might be called a right-handed axis. And if the phrase right hand reminds you of a right-hand rule when you are doing a cross product, that's exactly where it comes from. So with this representation, when you do x cross y, you get a direction of the z-axis. So it's right-handed axis is x cross y. Applying right-hand rule gives you z-axis. It's the way we've chosen to pick that semi-arbitrary convention. So, and this is the perspective view. So it necessarily leaves a bit of an ambiguity in where things actually are. And I guess if you want to avoid that ambiguity, you need to draw a couple more views. So, for example, I might draw a view from plus x, view from plus x. So imagine an observer who's sitting here, right in the direction of the x-axis, and just looking down the x-axis. For that observer, my y-axis will point to the right, and my z-axis will point directly up. and my x-axis is gonna point towards me, and just trying to point it towards you into the camera. And we have we use these two notations to indicate vectors that are either coming out of the plane or vectors going into the plane. It's meant to be evocative of an arrow. This is, you are looking at the arrow tip. Here you are looking at the arrow tail. So here the x-axis, it'll be coming out of the page towards you. So I would represent this as x-axis. And when you are viewing this way, this is necessarily going to collapse basically all the points with the different x values into this one plane. So you might need it on a second view from another plane, from another perspective. Maybe a view from plus y direction. So when you imagine you have an observer who is here and just looking down the axis, then imagining yourself in that place. So your y-axis will be coming towards you. That's how we set it up. And my z-axis is still going to point upward. And my x-axis, it should be pointing leftward. Okay. I guess between these two views, it might distinguish everything. Basically, if two points are so this view cannot distinguish when 2 points just differ in x value, but when you look at this view, you will see that when they do have different x value. So let me use this. Let's see. Oh, but I think for convenience sake of what I want to describe, I do think I want to describe just one more view. That'll help me describe one peculiar thing about a coordinate system I want to describe. So let me just draw one more view that's going to be complementary of the other three views I've drawn so far, and it'll frankly be duplicative of some information. So you could have a view from plus g-axis. And frankly, I guess the way we imagine our orientation, somehow I feel like I have a freedom to kind of rotate around as I view. So I can choose to rotate my point of view in such a way that I see my z-axis coming out of the plane and my x and y-axis the way they are normally drawn. So that's the third view that I can. And I think this degree of freedom, it frankly existed here and here too. I can just rotate these around and it'll still describe you from plus x, but somehow thinking of g as being upward direction and just locked into that thing. Yeah, and anyways, there's a rather thought-provoking question of when you look into a mirror, why do you think of yourself being flipped around the left to right instead of up down? But let me not get into that since that's not relevant for us right now. So this is the description of our three-dimensional axis. And when you imagine a point in this three-dimensional space, and you want to describe that point, it's perhaps easiest to describe that point in terms of its Cartesian coordinates. So you can imagine this point here. It's let's see, this point here. Then so this would be the y value of the point, x value of the point. I'm trying to, how do I match this up? I think this ought to be my g value of the point. So this point here, I can represent it in my other views here. So it would look like something like this, this, and this. So these would be g naught, x naught, not x naught, that's y naught. y naught. And in this view, there's no way to indicate the x value. In this view, I have x naught, t naught, and here I have x and y value of the point. And the Cartesian representation, I think it's easy to start from your intuition for the two-dimensional space and just to expand it out to just add one more dimension to what you already had. What's going to be a bit more challenging is the polar representation. There's a version of the polar representation that's quite easy extension of what you've had in two dimensions. Let me do that one first. So a version of a polar representation that that generalizes more easily from your 2D intuition would be this one, which is you keep everything that you had for your 2D plane. So all the descriptions that you had for your XY plane, you keep it. So for your polar representation there, you'd say, okay, I have this distance to the projection of the point onto my XY plane. So you have this distance. You could use letter R for that distance. Sometimes people use a different letter to say that it's not really the distance to the actual point. You are just reaching out to the projection onto the XY plane. And the polar representation included distance and direction. So I need an angle here. I could call this theta. Although with this version of polar representation, there can be different conventions. We might use a phi for a reason that'll be more evident later, and we would keep this portion as the third parameter needed to describe a three-dimensional point. This is a thing to be aware of. However many dimensions you have that many number of parameters to describe any given point in your space. So this is this representation, which uses the distance along xy plane, angle from the plus x-axis to that point on the xy plane, projection onto xy plane, and the g coordinate. This is what someone might call, or this is what everyone calls a cylindrical coordinate system. And to some sense, this is, it's really simple. It's a way of dividing up your three-dimensional space into really two-dimensional representations. So I guess one obvious version is this here, where you have it's a literally here you're literally describing the projection onto xy plane, ignoring the g coordinate. So it's this portion that's your old two-dimensional polar coordinate system, and you just tack on one additional dimension. And yeah, and I guess and another way this also limit to your three-dimensional thing into a two-dimensional plane is you can also think of this representation along this plane. The plane which contains the origin and the point that you're considering and the z-axis. So here your s coordinate would behave almost like the x coordinate that you had in the prior two-dimensional coordinate system, and your g coordinate would behave like the y coordinate system. So if you somehow wanted to know the distance to the whole point, then you would say, oh, the distance r is square root of s squared plus g squared. So that's another sense in which this cylindrical coordinate system is a way to divide up your three-dimensional representation into different slices of two-dimensional representation. All right, so that's one way of that's one version of the polar coordinate system, and the version of the polar coordinate system that took me really much longer amount of time to learn and gain a sense of familiarity with it's the spherical coordinate system, and and so so let me try to describe this from scratch here. I remember this is, I don't know why, the first place where I had to struggle with this system was in my astrophysics class, but it took me a while to fully comprehend everything in that. So describing the spherical coordinate system, I guess the thing understanding to start from is that you are dealing with one distance and two angles. So you are dealing with the distance from origin all the way to the point. That's just the distance. And let me give letter R for that. Or yeah, this could be R vector. Or if you imagine taking the magnitude, then that's the R distance from origin to the point that we are describing. And we need to pick two angles with which to specify a particular direction. And there's a convention that's been chosen. The first angle that we use to constrain where this point can be is the polar angle. It's this angle here, angle between my three-dimensional vector and the z-axis. And in physics classes, we give letter theta for this angle. So that angle can be represented, I don't think this angle theta can be represented on any of my drawings here. So if I were to draw this line and label this angle, or draw this line and label this angle, I'll bet you that these are not going to be equal to theta. Basically, the only way to get this angle theta is you have to think of a representation in this plane that contains the origin, z-axis, and the point. Only in that plane, which the angle, it'll be theta. So yeah, in none of these viewpoints, I can actually identify that angle theta. The only place where I can label it, but know that I can't quite measure it by taking a protractor to the drawing, is in this perspective view. But that polar angle, the angle between the vector and the z-axis, that's one angle that you use to start constrain the different places your point can be. Before that, with only this constraint, your point could be basically anywhere on the sphere of radius r. That's why it's called the spherical coordinate system. So once you specify the polar angle, then the only place where your point can be is within this circle here. So if you kept your r the same, you kept your theta same, and trace out all the different points your vector can be, it'll trace out a circle that looks like this. And it's going to be a circle that's parallel to the xy plane. So we can finish the remainder of the description of this vector in three-dimensional space by describing what we see in the projection onto the xy plane. So this point here, which is a projection of this point onto xy plane, will be part of the circle. So if you draw a line from origin to that point, there's the angle from x-axis to that line. This angle, which is called azimuthal angle, we give it letter phi. This is the azimuth. I think that's the correct term for it. This is the azimuth for that point. And I can represent this angle here in the xy plane. So I have this projection of the point onto xy plane. Projection meaning I just ignore the z-axis. And the azimuthal angle there would be this angle phi. And it's this spherical coordinate system where you do need more work visualizing and making sure that you can connect your spherical representation, which would be r phi theta. This is your let me just leave it that way. This is your spherical representation. And just because there are two different conventions out there, one that mathematicians use and one that the correct one that we physicists use, let me just give these actual labels, their names, because we call them by the same name. We just use different letters. This is your azimuth, and this is your polar angle. Mathematicians have those two labels swapped for some reason, for some unreasonable reason. So given this spherical representation, the task that if you are able to do it, then you can tell yourself that you understand this coordinate systems well enough is how to go from here to the representation that describes the x, y, z component. And this is where some visualization work is useful. Let me spend the next couple minutes just writing out the expressions for these components. So you're going to see these representations in a couple different calculations of electric field by direct integration that you'll see as part of this week's content. And it's one of those things that you don't really have to do. In fact, the whole thing about Gauss's law that you will learn this week is that it's also trying to avoid having to do that difficult multivariable calculation. But even so, it's good to know the basic descriptions in case you ever have to fall back onto them. So in going from the spherical representation to the Cartesian representation, the easiest component to handle is the z component. You can kind of guess at that because we treated the z-axis as the special axis. It's the first axis to which we determine the angle theta from our vector. So we can, you can imagine a right triangle in this way. Right triangle consisting of the r as the hypotenuse, and there you can draw a line perpendicular to the z-axis. That's one of the legs of the right triangle, and one of the other leg along the z-axis. That would be our z component. So considering that right triangle, you should be able to reason yourself that z component is given by r times cosine theta, since this is since the z component is the side adjacent to the angle theta. The x and y components are what I had trouble with when I was first learning spherical coordinate system. I wanted to say that x is r cosine phi and y is r sine phi. And what I'll tell you is that that's wrong. And the thing to make sure that you think through and make sure that it makes sense to you is that before we start addressing x and y components, we first have to take the projection of the point onto the xy plane. And in this act of taking projection, this side here, this is not r. This is, you can actually imagine this right triangle. This is the right angle, and this being theta, this should be theta. And this is the hypotenuse is r still. So this side here, the leg that's in the xy plane, that's the leg opposite to the angle. So the length of this leg should be r sine theta. So this is the length of the vector, or length of the projection of the vector on the xy plane. And using this as a starting point, then you describe x and y component. So when you work it through, your x component should be r sine theta times cosine phi, and y component should be r still sine theta. We are starting from the same hypotenuse times sine phi. So this is the translation from the spherical representation to the Cartesian representation. And we're not really going to use this too often or ever if you try hard at avoiding using it. But the reason I thought it would be worthwhile to cover this as a review is you do need to visualize the three-dimensional things quite a bit in this class as we do E&M stuff. And I thought, thinking through the, say, spherical coordinate system, that is a way to start practicing how to visualize a three-dimensional object, three-dimensional vector field like electric field, and things like that. I'll try to do both the review for dot product and cross product since cross product is so even though we are not going to be using cross products heavily for another 2-3 weeks, I think it's good to uh, I think it's good to just to do the reviews in one place because cross product is one of the things that you are supposed to have seen in physics 4a. So let me write down products of vectors. And what we'll be specifically covering will be the dot product and cross product. These come by different names. So in both of these cases, it's good to imagine two vectors in somewhere in space. So let me draw those two vectors. I have my vector A and vector B. We introduce them as arrows, and arrow is the I think most useful visualization of vectors. It has a length and it has a sense of direction, and um, and those are both important properties of vectors. Now, what is not an important property of vector is what position they are at. So vectors, the way we use them always refer to some kind of difference. So if we are going back to the coordinate representation before, you can imagine a tail of the vector being at the origin always. But even if you were to translate it off origin, the as long as you keep the length and orientation of the vector same, it would still remain the same vector. And when I say the words length and orientation, because as we define these product of vectors, we want to do it in a way that's coordinate independent. As in, even though I could, as we have last time, I could define an axis system. I could define x and y axis and describe these vectors in terms of the components along x and y. We can do that, and there are times when we'll find it convenient to do. But for us to talk about products of vectors, we don't need any of that. We can just observe the vectors that exist in space and characterize their direction. So the parameter that's going to be most useful to us is the relative direction between the two vectors. So call that angle theta. Then we, as in we physicists, define dot product this way. This is what I would call physics definition of dot product. By the way, the dot product goes by a couple different names. You might have seen the word inner product, or you might have seen the word the scalar product, which is not to be confused with multiplication by a scalar factor. These are all commonly used words for the same operation, dot product. The main thing about the dot product is that it takes two vectors and or it takes as this is not a symbol for dot product, but it takes as a input for two vectors, and then it turns those two vectors into a number, a scalar that doesn't have any sense of direction. And there are stories behind why sometimes it's called inner product, and I guess what I'm explaining is why it might sometimes be called a scalar product. So the physics definition of that product is if you have vectors a and b, then a dot b is equal to, and I'm going to introduce some common convention, which is So given this vector A, if I simply write down A without the arrow on top, what that conventionally means is that's the magnitude of the vector. Or if you really want to specify the mathematical operation, what this would be, would be the A dotted to itself, square root it. But I guess we need to finish defining the dot product for this to be useful. So this dot product will be A times B magnitude times the angle between the two vectors, cosine theta. And I'm saying this is our definition of dot product. You might have seen dot product introduced in a different way. I think in math class, you usually see the dot product in this form. This might have been how you saw it defined in a math class, sum of product of components. So AI times BI and add it up from I equals 1 to 3 or XYZ or however many dimensions. So this is how it's commonly defined in a math class. The biggest weakness there is that in order to talk about components of the A vector, AX, AY, AZ, you need a coordinate axis. You cannot talk about components without coordinate axis. And in this physics definition, we are trying to get as far as we can without having to define any coordinate axis. So we want to coordinate-free representation of the things we want to do so that we have the maximum freedom when we actually do introduce coordinate axis. So this is the definition of dot product. I guess as far as the mathematical expressions go, it's not too complicated. The maybe one part to take care is this theta. That should be the angle between the two vectors. And this has some nice properties, I guess. So a lot of these nice properties, they follow from the property of cosine theta. And you can also a little bit see it in the presentation here. So let me note some of those properties. I guess let's see, what do I want to focus it on? Let me focus on the algebraic properties of the dot product. So one is the commutability. I'm not sure if it's a commutability or if it's a commutability, whatever. This product commutes. What it means is when you have A dot B, that's equal to B dot A. You might look at me and say, that doesn't sound all that surprising. That's how we are used to dealing with the things. Product commute. What's so special about this? I mention it because we'll see other products where products don't commute. You might, let's see, would you have seen it? When you do linear algebra, when you look at the matrix multiplication, you will see that matrix multiplication does not, in general, commute. And you can see how this is related to this to the fact that the angle goes in as an argument of cosine, argument of cosine rather than sine or tangent. Imagine this picture here. So if you have A dot product with B, then you have this angle between them. So if you're trying to imagine what B dot product with A looks like, then it's like swapping the position of A and B. That's what commuting the two things looks like here. So if you imagine, okay, if I have B dot product with A, you can try to consider if this B dot A would be different from A dot B. And when you're answering the question, the number one resource is the definition. So when you go to the definition, you can see that as you swap A and B, nothing changes. So this is a scalar multiplication. So there you have a great intuition for just multiplying two numbers. And really the place where the order of A and B might matter is here, cosine of theta. So this theta could be positive, it could be going counterclockwise somehow, or it could be going clockwise. And if you remember some things about cosine, cosine is an even function. It's easiest to show on graph. If you are graphing what cosine of theta looks like from, I don't know, minus pi over 2 to plus pi over 2, then at theta equals 0, you have the maximum value of cosine theta 1. And as you go to pi over 2, the cosine theta decreases to 0 at pi over 2. And it does the exact same thing on the other side. Cosine of minus 30 degrees, it's same as cosine of 30 degrees, which necessarily isn't the case with the uh, it's not necessarily the case with the sine theta. So so with the cosine theta, this being an even function, when you swap the order, when you make a theta go to minus theta, nothing really changes. So 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 that's one property of dot product that you can actually get from the definition here. That's one of the things I like about the definition. And the other property, which takes more time getting used to, even though it's the property that you've known for quite some time. What I want to emphasize here is just how useful some of the rules that you've learned in arithmetic is. So here's a rule that you've learned in arithmetic. You've learned to how to distribute products. So distribution of product. In terms of scalar quantities, it works out this way. If you have scalar A multiplying with scalars B plus C, then what the distribution means is you get to distribute this product into the parenthesis thing. So this whole quantity is equal to A times B plus A times C. So this is something familiar you have seen before us introducing vectors. And what's nice about vector product is this is the defining property of field property of mathematical arrangement, where you have something that's like addition and something that's like a product. And that product quantity, unless it obeyed some sort of distributive property, we wouldn't call it a product. The fact that we call that product is the hint that the property that I outlined here also holds for vectors. So imagine this: if you have vector A multiplying with the sum of vectors B and C, what you can distribute this as is the product A dot B plus the product A dot C. So, and this property is going to be useful as we try to look at some of the consequences of this physics definition of dot product. The most important being, so you have seen this other alternative definition of dot product. You have seen maybe this in your math class, or maybe even your previous physics 4A class. Not everyone says First Kennedy about um, the coordinate independence of vectors as I am. Because oftentimes it is easy to define a coordinate system and use it. So most people don't dwell on how all these discussions, they don't require you to define a coordinate axis. But anyways, So this is what you might have seen as definition of dot product in either in a math class or possibly even physics 4A. So when you have A dot B, so the compact form I wrote before is to say, okay, that's the sum over I from 1 to 3, and the product of AI times BI. Or if for a three-dimensional space, this would boil down to AX times BX plus AY times BY plus AG times BG. And it's reasonable to wonder, so which is which? Is my dot product this quantity here? Or is my dot product this quantity here? And the short answer is both. So you ought to be able to prove, starting from one, that that the two statements are equivalent, even though they are not stated the same way. That you should be able to show, starting from one of the starting places, that you can actually get an expression that looks like in the other one. Now, technically speaking, this is a wholly equivalent system, if and only if, and it ought to be able to prove, starting with this mathematics definition of that product, that this is something that you can expect from this. Um, but that proof is a lot harder than what I'm gonna do. So, and this is really the other reason that I call this the physics definition of that product. If we need to prove some relationship between quantities, it's actually a lot easier to start from here and then and then come up with some expression that we can use to estimate some things. So what I'm going to do is I'm going to try to write out A dot B and somehow break down vectors A and B in terms of their components and then work through these steps. So if I'm imagining A and B as vectors, so the A vector would look something like this. It's going to have component along x times x hat plus component along y, again times y hat plus ag times g hat. And let's see. Yeah, so this is the expansion of the vector notation for A in terms of the vectors, vector components of A. And the vector B is also similar. I can write it down as, wait, what do I want to write it down as? Oh, yeah, the capital A, that's the component. So it should be bx times x hat plus by times y hat plus bg times g hat. So with this representation and armed with the knowledge of the commutative property, we can actually do this explicit calculation. Let me set this up. I have A vector dot product with B. Now, if I'm simply looking at this expression here, I can say that's AB cosine theta. Now, that doesn't really help me prove the statement that I want you to prove. So what I'm instead going to do is I'm going to write out what vectors A and B are in terms of their components, because I say that I'm gonna get back to the components. So you imagine that in some space you define the coordinate axis. I have some kind of coordinate axis, and I can just start writing down different forms of the same thing that I've already written down. Just undo to the point. So I'm going to expand out vectors A and B in terms of their components. So I can actually write A as, okay, that's component along x times x hat plus the component along y times y hat plus the component along z times g hat. That's my vector A. There's nothing wrong with writing it in this longer way. Let me just finish doing the dot product. This is dot producting with, again, the x component of B plus the y component of y vector plus the g component of the g hat vector. And so it's a potentially long multiplication step involving quite a few unknowns. So let me do it this way. I'm going to write 3 pairs that I see with AX, and then I will note some things that you will be seeing over and over. And then for calculation of AY and AG, I'll do it more quickly. So let me write out the product with the distributed terms. So I'm just going to write the 3 products that this AX gets distributed into, with the X hat, with Y hat, with G hat. So I have AX, X hat, times BX, X hat, plus AX, X hat, times BY, Y hat, plus AG, G hat, times BG, wait, sorry, H. I confuse myself with these components. AX, I'm just sticking with the axis. AX, X hat, times BG, G hat. All right. So here we can use the commutative property of not of the dot product necessarily, but of the numbers of the scalars, and the scalar multiplying to other vectors and scalars. So whether I have x hat be as it's here, or if I have a b times x hat, it's the same thing. That doesn't change anything. So I can imagine pulling these coefficients to combining it with the first coefficient. So with this dot product, really what I'm working out is x hat dot x hat, x hat dot y hat, x hat dot g hat. And let me apply the definition. I have a one vector dot product with another vector are product of the magnitude of vectors times cosine theta. Here with x and x, cosine theta is 0. It's the same vector. They're pointing to the same angle. So I have for the first term ax, bx, and nothing else. I mean, there's times 1 plus. Now it gets interesting with x hat and y hat. So if your x-axis is coming towards you, then your y-axis might be going to your coming towards you. Yeah, let me have it go into your right. So then x hat dot product with y hat, they are perpendicular. So you get cosine of 90 degrees. So this x hat dot y hat, that's 0. And since the dot product is 0, it doesn't matter what the coefficients are. ax times by times 0 is 0. So I have 0 here plus x hat dot product with g hat, that's another 0. Because the x vector, so pointing towards you, and the way I was describing my coordinate axis, g-axis pointing directly up, still perpendicular. So I hope you are beginning to notice a pattern. So when you have this dot product, you need these unit vectors to be the same 2 unit vectors, both x hat, both y hat, both g hat, in order for this product not to vanish. When it's anything different, it'll vanish. So for the rest, I don't really have to write out 3 more terms and then 3 more terms. I can just okay. Let me just do the one term that I know won't go to 0. So with the y hat, it's gonna be ay times, and the only thing it can dot product to 2 and not go to 0 is by, y hat. So it's going to be ay times by times, and dot product of two y hats will give you 1 because it's a unit vector. And done with the first y hat. Let me add the contribution from z hat. So it's the same deal. All the other dot product will go to 0 except for the one with the z component. So you have az bg times cosine of 0 or 1. And you can see that as I clean this up and write it out, ax bx plus ay by plus az bz. And that matches the definition of that product that you have learned before. And um, and yeah, and this is the dot product. There are other visual ways to interpret it. You could think of it as so dot product is you imagine taking projection of this vector along the other vector, and you could describe the dot product as a product between this projection vector and the oh, I guess once you've taken the projection, then you just multiply the magnitudes together. That'll give you the dot product. I think that's good for dot product. Let me give you the physics definition of cross product. In addition to because cross product is one of those things that a lot of people do forget, or in physics 4A, the kind of context where cross products come up. The it's possible to do them without cross product. So cross product is one of those things that people, depending on what previous math or physics class you took, the specific one with a specific instructor, you might not have seen it. And a lot of times, even the people who have seen it, people who've taken my physics 4A, I find that people do forget it. So let me cover the cross product. And I think it would be good for me to start out with the physics definition of cross product, because we have a way of defining cross product that's independent of coordinate axis. So if you imagine two vectors a and b, let me just draw them the same way that I've drawn before. Then this is how you would define cross product. You define cross product by associating a plane with these two vectors. In fact, in most contexts where cross product comes up in physics, you can somehow associate a plane with whatever context the cross product is coming up in. So now the challenge is, as you are defining that plane, or I guess in terms of the screen, this plane, as you are defining the plane, you need to describe the direction of that plane in terms of a vector, an arrow. So the challenge is, how do you associate an arrow, a unique arrow, in such a way that you can associate a single plane with that unique arrow? And I hope you can quickly see that if we are picking any vectors along in the same plane as A and B, then that's a hopeless task, because there's going to be so if this is my plane, there's an infinite number of vectors in that plane. I cannot use one vector to associate that with a plane. This is where you have to go out of the plane and realize that, oh, it's so if I want to uniquely define a direction of a plane, like imagine a vertical plane where my hand is touching, then a way to uniquely describe that direction. So none of the vectors and lines in the plane will do. But if I have a line that's perpendicular to the plane, then I can describe the plane as the plane that's perpendicular to this line. So that's the starting point of defining cross product. Wanting to define, wanting to associate a single vector with a plane. Now, as you're, so with this plane here, plane of the screen, as you're looking for the vectors that are perpendicular to the plane, you have two different vectors. You have a vector that's coming out of the screen towards you, and you have a vector that's going into the screen away from you. Both the vectors would be perpendicular to the plane. So, but we need a unique choice, a single choice of a vector that'll somehow work for us. And that's the place where so far we've relied on geometry, we've relied on mathematics, nothing arbitrary. We are trying to, so that's where we started, and this is as far as we'll get if we're insisting on nothing arbitrary. And at some point we have to make an arbitrary choice between two possible directions of vectors. And what matters here is that everyone in the world agrees to one particular convention. And when I have an interactive lecture, this is the point at which I usually ask people, could people please raise their dominant hand? And most classes, 90% of the students will raise their right hand. And that is frankly where the right hand rule comes from. Right hand rule is a way to somewhat arbitrarily choose between two possible vectors, choose one unique vector. It's arbitrary, but it's the rule that everyone agrees to. So that's how it works. But you could do the exact same thing with your left hand, and then that would be left hand rule, and that would be the convention that no one else is using. But if you wanted to somehow rebuild all the vector algebra, including the cross product using left hand rule, you can do that perfectly fine. The biggest challenge is getting other people to do the same thing that you might do with your left hand. So I'm just going to use the right hand and do the right hand rule. So the role of the right hand rule is just to pick between the two vectors. So you have a choice of either vector that's going into the plane. I hope people remember these notations. You have to imagine an arrow. This is like an arrow tip that's pointed towards you. So it's a vector out of plane. And this X is meant to evoke the idea of a tail end of an arrow. So it's as the vector is going away from you, you see the tail end. So we have the choice between these two vectors. Do we choose the vector? They are both perpendicular to the plane, and which way perpendicular do you choose? And with the right hand rule, this is how we choose it. We orient our right hand. By the way, there are different versions of right hand rule out there. I'm going to demonstrate the one that I like, which is the version that uses the whole hand. There's a version that uses 3 fingers. I don't like it. It most particularly, it doesn't morph naturally into the other versions of right hand rule you'll see this semester. When you use the whole hand version, it morphs naturally into the other versions that you will see when we get to magnetism. So I'm going to use this. Whole hand version, you orient your hand in such a way that your hand points in the direction of first vector. So as I'm writing down my A cross B, A is my first vector. So I orient my hand towards A, and I orient my hand, rotate my hand in such a way that as I curl my fingers, my curled fingers curl in the direction of B. And okay, this is not doing it, so it has to be A cross B. So I start with my hand pointed towards your right, so that my direction of my hand matches the direction of arrow on the screen. And when I do A cross B, the direction of my thumb out of screen is the direction of the arbitrary choice that we have chosen to use out of the two possible choices. So A cross B gives you a vector out of plane. And try yourself, pause the video for a bit, and try your own hand. get your A in the direction of the vector you see on the screen, and then orient it so that it's A cross B. By the way, I'm doing this from perspective of me looking at the screen, A cross B, and my thumb is pointing towards me, which is out of screen. And the amazing thing about right hand rule, whether I do this orientation for your perspective or I do it for my perspective, it actually works out. so so yeah, so A cross B get so this direction of the thumb is meant to pick between two possible directions, one way perpendicular or the other way perpendicular. This picked one way perpendicular. So that's a part of the definition of dot product. So there's a so so let me state that portion of the definition. So I have one definition, which would be the direction given by right hand rule. There's no real better way to say that in a single written sentence. That's one. And now after you have, so the physics definition of cross product, it comes in two parts. And it comes in two parts really because the cross product gives you a vector back. And whenever you are specifying a vector, you need magnitude and direction. This is in contrast with the dot product. Because the dot product resulted in scalar, all you needed was the value of that scalar. You didn't need to know the direction of the dot product. But with the cross product, there's direction. And the direction is what takes the longest to state. That's why I've taken 10 minutes to do it. So that's the first part of the definition. The second part of the definition deals with the magnitude of the cross product. So the magnitude of cross product, as a matter of definition, the physics definition, is that the magnitude is defined as the product of the magnitude of the vectors, A and B, and times, if these vectors are in space, there's some angle theta between them, and what you're multiplying here is a sine of theta. And if I'm strictly being careful here, it should really be it should really be the absolute value of AB sine theta. Yeah. So this is the second part of the definition of cross product, giving the magnitude. And there's a lot of ways you can contrast dot product A dot B with the cross product A cross B. One is the one that I just gave, that dot product results in scalar, cross product results in vector. And the other is with the dot product, I made a point to say that these products commute. A dot B is equal to B dot A. And with the cross product, if you apply through these definitions carefully, you will see that they don't commute. I mean, in the magnitude portion, maybe it does. If you swap A and B, nothing seems to change. Okay, let's leave that alone for now. But look at how we describe the right-hand rule. Because as we are applying the right-hand rule, we talk about first vector, second vector, so the order seems to matter. So let me just try applying the right-hand rule, treating B as the first vector. So I'm imagining what would it be B cross A? Will it be same as A cross B, or will it be something else? Well, let me use right-hand rule. So I'm orienting my right hand along the direction of B, as seen by you. And I need to orient my hand so that I can curl my finger in the direction of A. Oh, I guess it's okay. So B cross A is thumb is pointing towards me, or from your perspective, the B cross A is into the screen. So B cross A gives you this direction. So B cross A is not equal to A cross B. In fact, since the magnitude won't change, what with the B cross A, the only thing that changes is the direction. It's in the exact opposite direction from what it was. You can say minus B cross A is equal to A cross B. Or this is what sometimes we call, you could say that they anti-commute. That's used more in upper division level places. But I guess the thing to remember is when you swap the order of product for the cross product, the sign flips. It's an implication of the definition as defined using right hand rule. Now, so this is what I'm calling physics definition of cross product. And as you are listening to this, if you are thinking, this doesn't seem to have anything to do with the definition I've heard um, in the math class. Let me show you the connection, how you can get from the physics definition to the version you might have seen in your math class. So the version that you might have seen in your math or other class is if you have vectors A and B, so A can be represented as AX x hat plus AY y hat plus AZ z hat. And by the way, for the cross product, you do need all three dimensions. You simply don't have a cross product with only two dimensions. That's another contrast with the dot product. B vector is BX plus BY y hat plus BZ z hat. Given these two vectors, the cross product A cross B is, let me see if I can remember the whole thing in one shot. It's going to be equal to AX. Sorry, I messed up on the first. It's going to be AY BG minus AG BY x hat plus AG BX minus BG AX y hat plus AX BY minus AY wait, did I confuse myself here? I didn't really. AY BX z hat. And it doesn't change any of the result, but just so that it won't look like I confused myself, let me just swap the order of these two letters. This is a product of two scalars, so they commute. I can swap their order as much as I want to. It doesn't change anything. And I think depending on my mood, I either write these things the way I've written it for my y component, or as I've done it for my x and z component. And there's a way in which you can memorize it. That's how I have it memorized. If you see this cross product or outer product in an upper division setting, you could actually write this super, I guess, you can you can use something called Levi Civita symbol, which is epsilon ijk, to express your cross product this way as the sum as let me write it out and then I'll just erase it. Sum of I going from 1 to 3, j going from 1 to 3, k going from 1 to 3, and the product that you're looking at is AI, BJ, and the RK hat. Multiplied to the Levi-Civita symbol IJK. And this is defined in such a way that this is 0 if any of the three are the same. If I is equal to J, or J is equal to K, or I is equal to K. If any of these are true, then it's 0. and it's equal to +1 for what's called a cyclic permutation. For cyclic, so that would be things like if ijk is 1, 2, 3, or 2, 3, 1. You can see how they go in a cycle, and in that case, this is +1, and this is equal to -1 for the anti-cyclic permutation. That would be like 2, 1, 3. So it looks like it's going the other way, or another example of anti-cyclic permutation would be, I think, let's see. Let me write down 3, 2, 1, and yeah, that's also anti-cyclic. And that's how I actually remember these signs. So once that have plus sign, they go in that cyclic order: y, g, x, g, x, y, x, y, g. The ones that have minus symbol, they go in anticyclic order: g, y, x, or x, y, g, x, g, y, or I guess x, y, g, and y, x, g, or let me x, y, g. So going in anti-cyclic order. So, so okay, I promised the connection between this. So even though you might not have seen this, the upper division level stuff about Levi-Civita symbol, but you've definitely seen the component by component version. This one, however you have it memorized. There's actually a neat way to memorize this that doesn't involve this weird symbol. You can memorize this as a kind of a determinant of 3x3 matrix. There's that method out there, and I think I showed it in one of the lectures. You can see it there. Let me end by showing the connection between the physics definition and the component definition that you see maybe in your math class. And the way to get the connection is by figuring out what are these cross products: x hat cross y hat, y hat cross z hat, and or so the what you what the information that would help us draw the connection between the two is what is this cross product: a unit vector, a coordinate unit vector, cross product with another coordinate unit vector. So if you have something like two unit vectors that are the same, like x hat cross x hat, then I hope you can see that's equal to 0. Because here, the magnitude will be 0. Because sine theta, sine of 0 is 0. Now, if you have, so let's say you have x hat, and I want to figure out what is x hat cross y hat. Then, so this is the three-dimensional coordinate axis that's usually drawn. So if I say this is my x direction, and this is my y direction, then my z direction will be out of the board. And what it really is I don't know how often we emphasize it. This is a right-handed axis. That's because we use the right-hand rule itself to define our third axis. Because if someone said, oh, z-axis, it goes into the plane, not many people would raise an issue with that. You see all three axes are perpendicular to each other. So does it matter what direction z is going? Well, it matters whenever right-hand rule matters. So here, when you have x cross y, you have the thumb coming out of the screen. So we have to associate that with our positive z-axis if we want our right-hand rule based direction of a cross b to coincide with this. So we say, okay, x hat cross y hat is z hat. And once you have defined your axis to be compliant with the right-hand rule in one way, then the rest will fall into place. try this out. Try out what you would get if you take the cross product of x hat cross g hat, and when you work it all through, you should get, so pause it if you need time, and when you're all done through, you should get minus y hat. And there's a few more combinations that you would have to work through. So let me leave this as an exercise for you. So you can actually, so once you have all the relationships between the unit vectors worked out, there should be 6 of them, basically 9 minus 3, because 3 of them involve the same vector twice. So once you have those 6 relationships, then when you have this A cross B, you are equipped to expand it this way. Write out the A vector in terms of its component, AX x hat plus AY y hat plus AZ g hat. Cross product with B vector, BX x hat plus BY y hat plus BZ g hat. And as weird as cross product is, it still obeys the rule that we said applies to products, the distributive property. The distributive property that we described still applies. So you can distribute this AX x hat into cross this and cross this and cross this. So there will be 9 products in total here, and you can all work them out because it's basically going to be some coefficient times a unit vector plus another unit vector. So this product will be 0 because x hat cross x hat is 0. But AX cross product with BY y hat will not be 0. The cross product of the unit vectors will result in G hat. So you have AX times BY times G hat. And in fact, that's this term here. So, and when you have X hat cross product with the G hat, then you have, you have minus Y hat. And so you have AX times BG, or minus AX times BG Y hat, and that's this term here. So you can work this out component by component. So considering product of this term with all 3 terms here, I got 2 of the terms that I have in my cross product formula. And you can get the remaining 6 by considering remaining 6? No, you can get the remaining 4 by considering distributing this term into the B vector components and this term into the B vector components. It's a fun exercise. Okay, maybe it's not fun. And this is quite complex. Well, not complex, complicated. And this is probably the reason I prefer the physics definition of cross product, because this connects more easily to the physical things you will see. So later on, when we do magnetic force, you're going to see a magnetic field setup and some charged particle that's moving. And it's so much easier to figure out the direction of the magnetic force by using this definition and using the right-hand rule, rather than using components, unless some question gave you the vector components instead of giving you the description of where they point. So yeah, I think that's all the time we have to talk about cross product. I probably should redo a shorter version of this at some point.